our lecture. This is number 11, problem session 11. I counted it up today. We're going to have 30, so we're not quite halfway through the course. And the halfway point is roughly the midterm exam next week. So once again, let's see, problem session February 28th will be in Keller Hall. In Keller Hall, 3125 at 4 p.m. Live and in person. And then the midterm exam will be on March 2nd, which it was Thursday, again in Keller Hall, 3125 at 4 p.m. to 5:15. So I haven't made the exam up yet, so it's a little premature for me to tell you exactly what's going to be on it. Generally, I try not to make the exam include the very latest material, but of course, we get to the end of the semester, the final exam ought to include everything. So I'll let you know what material it's going to include, and probably through this problem session would be a fair way to talk about it. But in an hour and 15 minutes, which is effectively 75 minutes, roughly 3 problems. Now you can go look at other exams on the web page that I gave you early in the semester. The problem there, please, the problem there is that I used to teach with 2 midterms, an early midterm, midterm 1 and midterm 2. So if you look at midterm 1, it will include material, that'll be fine. You will have covered it in this course. But if you look at midterm 2, you're going to say, oh, we haven't had that. Please don't come back to me and say, are we going to have the same thing as on the midterms that you put on the web page? I will tell you right now, what we're going to cover this year in this midterm will be up through today, okay, up through the beginning of power system security. Whatever we cover today, because the exam is next week, okay. So every year a student looks at an old midterm and goes into a panic. We haven't had that. Well, that's because sometimes I taught the material in a different order. Anyway, so think of this year's lectures and problem sessions up through today, okay? And remember your homework, 05 is due March 3rd. Okay, March 3. All right. Let's start talking about today's topic, power system security. This is a topic that comes into both the planning, construction, if you will, of a power system, but especially into the operations of the power system. I always like to talk to my students in certain. I give a lecture every year for non-engineering students. It's it's a course that's run for lawyers and economists and so forth. And we teach it through the University of Illinois. We teach it in Chicago. I was talking to them about a Prussian military general named von Moltke. And von Moltke made this statement, and if you do any reading of military history, you'll come across this statement where he said, no military plan survives first contact with the enemy. Okay, so he wrote this in the 1800s when wars were fought on horseback and, of course, foot soldiers marching. There were no tanks, there were no airplanes. And so the armies, would send out people on horseback to try to find the enemy and try to come in on their flank or come in behind and so on and so forth. But what he was saying was that if you had a brilliant plan for how you were going to attack the enemy, as soon as the two armies contacted each other and started, they were shooting guns and cannons and riding cavalry into the other cavalry and fighting with swords. As soon as you made contact with the enemy, your brilliant plans that you might have spent months and weeks or putting together went out the window. He didn't use those words. He just said that the plan doesn't survive because the enemy doesn't react the way you think, or thought, I should say, because you're done planning, and you say, well, when the enemy contacts them, we're going to do this, and all of a sudden you make contact with the enemy, and the enemy does something else, and now you have to react. And what it takes to be a good general, think of Napoleon in Europe. It takes somebody that can react and do the right thing in the heat of battle, so to speak. Well, in a power system, you plan the power system, okay? And you're planning. And there are groups that do this in most of the major ISOs and the big utilities. They have planning. And so they might look up 5 years or 10 years ahead in the future. And you consider such thing as load. Is the load growing, and where is it growing? Where are the houses being built? Where are the apartments and businesses? Where are the factories? Or, where's the industrial load? And we look at new generation and new transmission. Obviously, you need new distribution, but that's just dictated by where the load is. And you don't usually build distribution too far out because it's expensive. And if somebody starts a housing development, well, you want to put the distribution in just about the time they start construction or a little bit before. But transmission might take 5 years, 10 years, 15. We can even put 20 with a question mark. Well, you want to look way out into the future. Okay, so you build this system and you start construction. These big transmission lines, big substations, big generators take 10 or 15 years to build. So you've got to plan way out. But now we come to operations. So that means real time. Or we could say right now. And the system that you thought that you were going to have, that your system planners told you, doesn't come. Not because of delays in the construction or anything else, but the operators of the power system suddenly are confronted with outages and occurrences that you didn't plan for. You cannot plan for everything. You really do, you really can't. And so all of a sudden you realize that it's a hot summer day. The load is really, really heavy, driven by air conditioning. That's what drives power system peak is almost universally driven by air conditioning throughout the world. And maybe all of a sudden one of your big generators fails. At the same time, you have some transmission out for maintenance on a big transformer, let's say. There's combinations of things in the system, and you're looking at a situation that you can't, maybe you didn't plan for exactly. And so the operations people, they have to do, sometimes it's called operations planning, but they do a series of things in order to keep, and what we want to do is we want to make sure no generator outage and no transmission outage causes a blackout. Now, that's pretty drastic, a blackout. But a blackout occurs typically, here's a typical situation. You'll have a transmission outage, and you'll have some overloads and some low voltage. And then, if you haven't planned it right, the first outage causes the system to overload someplace else, and suddenly that system, let's say, has a low voltage, and it opens some other equipment, and you begin to have what's called a cascading outage. Outage number one causes the system to overload, and that causes outage number two, which is a result of that overloading. So now you have two outages, two lines out, or two generators, or some combination. And so one outage causes another, and pretty soon, generators, if there's just not enough generation, it's going offline. The generator's shut down because the frequency starts to drop. Or, if it's a bunch of transmission outage, generally that results in voltage collapse. Voltage is going down too low, and the system shuts down. The last big blackout that we had in the United States was 2003. The transmission outages started in Ohio, and it affected much of the Midwest, Ohio, parts of Indiana, much of Michigan, parts of Canada, New York State, over to and including New York City. Now think of the timing. 2003 came right after, 3 years later than the airplanes hitting the World Trade Center. And when that outage occurred, I talked to my daughter who works for a moving agency, and they have moving agents all over the country. I said, do you have somebody in New York City I could talk to? And she put me in touch with this fella, and he said, yeah, he said, people are on the street, the subways have stopped, the traffic is just completely stopped, there's no, the street lights are out. And he said, everybody is afraid that it's been another attack. Well, it wasn't. It was just a power outage in Ohio that affected New York City. If you watch the lecture notes, in there I have the two pictures that were on the covers of Time magazine, and I thought it was so good. One of them is 1965. There was a blackout. A bit of personal history, 65. I was in the electric power engineering program at Rensselaer Polytechnic Institute. That blackout started my whole career. And for a lot of people that are contemporaries of mine, I can name several friends who are now close to or at retirement, who career started with developing technology and software and so forth for preventing blackouts. So we have this this problem of preventing a blackout. And again, you like the battle scene. You make contact with the enemy. Things happen that you weren't planning for. Well, you don't want a single outage to cause something. And so what we do, and we do this in planning. Let me go back to the case of planning. How to tell if the power system, and I'm going to use the word secure rather than use the word reliable, because the word reliability studies means that we're trying to factor in probabilities of outages, and we're trying to study many more contingent cases. But let's say how to tell if the system is secure, and what we mean is no single transmission outage results in an overload on a line or transformer, or let's particularly what we're worried about, we're just going to say a voltage violation, typically low voltage. So no single transmission. So if a transmission line goes out, none of the flows on the system become too large, and none of the voltages drop too low. And so what we're saying is that the system, and this all the primary way that you get reliable operation in a situation like this, assuming that you've followed standard practices that have been worked out over years and years for the best way to construct the line and build the equipment and build the the relay equipment and so on. So the best way then to provide reliability is redundancy, and redundancy simply means that you're overbuilding it to some extent. So you're going to overbuild it, and overbuilding it means you have extra transmission lines. We'll see this in a minute. And again, no single generator outage results, it's the same thing up here, but it also, we can say, results in another generator out. So it doesn't result in an overload or a voltage violation, and it doesn't cause another generator to go out. If you don't have enough generation and you lose a generator, all the other generators are going to try to make up for it. We'll get to that in our study of generator frequency control. And if you have too few generators, and or they're all the ones that are operating are right up near their max, and you lose one, maybe you lose a 700 megawatt generator. Well, where is that 700 megawatts going to come from? Well, generally it can come over connections to other utilities, assuming that they have a lot of extra capacity, but it should come from your own eventually. And if you don't have enough extra capacity, called spinning reserve, then the frequency is going to start to drop. And where this is a big problem is on systems that are built on islands. My example, because I worked a little bit on a system for the island of Puerto Rico in the Caribbean, U.S. possession. People there vote in U.S. elections, so I'm not sure. I would say they're citizens. certainly that Puerto Rico, and it does not have any connections to anywhere else. It's too far distant. And therefore, if the island of Puerto Rico, if they lose a generator, they really better have extra generators online, or they better have the ability to shed load very quickly. And there are schemes where if you lose a generator, the frequency goes down, they can do what they call under frequency load shedding. And that's a way of basically compensating. But you don't like to do that because you got customers that just on a nice hot afternoon, you turn their power off. They can't run their air conditioners. The lights are out, and unless they're going to go out, well, they can go out and cook on an outdoor grill or something, but they can't. People don't like that. And guarantee this happens all the time. They'll go to their government representatives who get up in the legislature and scream and yell about the electric utility and that it has to change and new management has to be put in. As we like to say in America, yada yada yada. They just go at it. Posturing, it's political posturing, but it happens every time. In the big blackout of 1965, there was a senator from, I think, Montana, who said, it's time to nationalize. Now, the United States is a very capitalist country. All of the electric utilities were private companies, except for a few government utilities like Bonneville Power and TVA and so forth, and municipals. But the big utilities in all the big cities were private companies making profit. And he said, it's time that we basically nationalize, meaning the government would just go in and take over. Well, this idea was floated and died instantly. But that's the other thing. I'll clue you in. The other thing that happens is that the stock and the stock market for these companies will dive. And I know somebody that the outage in '65, the stock of one of the companies in the East Coast went way down. He went out and bought it the next morning. And a few days later, it went right back up, and he made a nice profit by selling it off 3 or 4 days later. So keep that in mind. If you go out and lose money on it, don't blame me, because I can't guarantee. But that is a typical situation. Anyway, you don't want blackouts. You don't want the customers screaming. If there's anything, the politicians will come in and do things that you don't want. Now, let's also talk about when our power systems vulnerable. When are they vulnerable? Well, at peak load is the most vulnerable. Usually let's say mid-afternoon in the summer. We had a situation about 1996 in the northern part of the United States, where there had been a thunderstorm, a very, very electrical storm that had gone through Minnesota, Wisconsin, parts of Canada, and knocked out one line after another. Minnesota actually divided into multiple electrical islands and then had to be connected back up. And the result of those outages caused power plants to be offline. Plus, this was a time when nuclear plants were being refueled, and there was an alarm put out, an alert all the way from Minnesota to the Atlantic Ocean coast. So it went all the way across the northern United States. Overloads all the way across. And shortages. And the danger at that point was that maybe one more power plant or one or two more transmission lines go, and we could have had a national outage, which would have been unprecedented. Normally we have blackouts, but they don't go too far. They don't go too far, although sometimes they get into multiple states and so forth. The other thing, and we'll cover this when we get to markets, is that the market reacted and the price of power went. This is, you talk about volatility. The price didn't double. The price didn't go up by a factor of 10. The price of power went up by a factor of 100. That's how the market reacted. There was just no power available, and those people that were willing to buy it, they're willing to sell it, and the people wanting to buy were so desperate that the price of power went from, let's say, roughly $100 per megawatt hour. It went all the way up to around $10,000 per megawatt hour. So that's 100 times 100. Extremely volatile prices. I think that market kind of situation has been brought under control. But when we get to markets later on in the course, we'll see how that could happen. Maybe I can cook up an example for you that will show that. But in any event, when are they? Their peak load, and that particular outage, it started the night before, but the real peak in price and so forth happened in the mid-afternoon, and it was a hot day. It can also, when are they most vulnerable? When equipment is out for maintenance. Now there's a language, and we call these a scheduled outage. Scheduled outage. The people from the substation group of your company call up and say, we've got this transformer and we've got this problem, and we have to take that transformer offline for 2 days while we bring a crew in and we work 24 hours a day to replace something on the transformer. And if we don't do it, the transformer is gonna overheat and possibly be damaged. So we've got to schedule that. And the people in operations are saying, please, no, but they have to do it. But they say, okay, we're going to schedule it for Monday and Tuesday because those are the lowest level of load. The load tends to build towards Friday. Or maybe they do it on a weekend. Maybe they say, okay, you're going to have to pay your crew double time or triple time, meaning double or triple the hourly wage, and we'll take the transformer out on Saturday and Sunday. And that's done. Same thing for generators. There was a time in the danger. The worst problem with taking generators offline is if you take them all off at the same time and the load doesn't go down as you expected. So you would expect load to be lower in the fall or spring. And in the summer, it's at its peak, and in the winter, it's going to have a heavy load due to heating and so forth. But in the fall and spring, people have their windows open, their air conditioning is off, the heat is off. Well, the load should be less. And if you're depending on that, you take 3 generators offline, and then the temperature outside starts to creep back up into the 90s and up over 100. People turn their air conditioners back on, and you're in trouble. Okay, so you talk about scheduled outages. Now, so what we're looking at these vulnerabilities, and what we do is, here we are. I'm going to draw a timeline here. Timeline. And here we are right now. Okay, so let's say here I am, and I'm going to say I'm out by 10 minutes right here. Right now, I measure the power system. So I measure the power system. We will talk about that in the later parts of the course, how you do that. But we literally build a model in the computer, build a computer model which is the same. You try to make it the same as the system is now. The same generation, the same loads, the same flows and voltages, as close as you can. And what you do is you take this model and you say, well, what happens if I lose this transmission line? And I'm going to show you some results, and you're going to run some of these for homework. And you're going to run them on a program that I have. So you take the model and we subject the model to what if. What if line 1 is lost? And what we do is we take the model, it's all set up, it's all been initialized to the existing condition, and now we remove line 1 and we resolve with line 1 out. Now when you do that, when you take that line out, you're going to find that other lines have heavier loading than they had it earlier, and bus voltages drop. Now, and so you say, okay, I did that for line 1, and none of the other lines went into overload. None of the voltages got to be too bad. Good. Then put 1 back in and take line 2 out. Take line 2 out. And then repeat. And you repeat this over and over and over. Now, if you have a typical network, a good rule is to say, if I have n buses, then I am probably going to have like 1.5 times n lines in the system. This might be a number like 1.7 for a very dense system. I could have a system with, let's say, 2,000 buses. Then I might have 3,000 lines. So I got to go through this procedure 3,000 times. That is very unrealistic, and we will talk later about some techniques to try to speed that process up, try to get ahead of it, and predict which are the worst cases. And each outage is called a contingency case. So we call this contingency analysis. Or it's got a name that better name is security analysis. And that means check the security of the system. Now, it turns out that if you're doing this for a planning system, Okay, if you're planning to build a system, you do the same thing. Only you say, okay, I'm going to adjust the loads for 10 years out. I'm going to put the new generators in, and I'm going to put the new transmission lines that I think I need, and then I run the contingency analysis. And if it's a miserable failure, then I haven't done the right thing. I maybe need to put a different set of transmission lines. I need more transmission lines or more generators and so forth. Contingency analysis is the kind of thing that technically you ought to do that for any business that you're in. You ought to say, well, what's going to happen to my business if the delivery of new parts is delayed by 3 weeks? What, am I going to go out of business? If so, maybe I ought to have a stockpile, and so you have to try to optimize the amount that you have in stockpile. So if you're someday going to go and get the dreaded degree known in the United States as an MBA, Wallenberg takes a dim view of students getting an MBA real quickly in their careers. My view is that if you're an engineer, get a master's degree, which is what I think most of you or all of you are doing. Get a master's degree at least. Go to work for a while. After you've worked for 10 years and you have a master's degree, then go get your MBA and you'll know what you're doing. If you go get an MBA right after you've got your bachelor's degree, you don't know anything about business, and they're not going to give you a management position on day one out of college, okay? We used to have a lot of students that came and said, we're going to get a master's degree in business administration right out of school so that we can go right into management. No. Anyway, an MBA would teach you the same thing. That any business has got to do some sort of contingency analysis thing. What if our warehouse burns down? How will it kill our business? What can we do to get back into operation? All those kind of contingent events. And the power system does it way out 10 years ahead, but it also does it. Here's my timeline. So here's now. And let's say I do it every 10 minutes or every 5 minutes. So I run that contingency analysis. I run it here. Looking ahead, I run it here. I run it here. So this is contingency studies. Every 5 minutes, depending on the power of your computers, you keep running it. And why do you have to keep running it like that? I mean, why run it 5 minutes later? The reason is that the load may have changed or flows shifted for some reason. And if you've put a new generator on, the system is in constant change. So you want to rerun this contingency analysis over and over and over and over again. My understanding is that the big ISO, the independent system operators, simply have stacks of computers that are nothing but a large printed circuit board with a lot of memory, and they're on a bus. And each computer can run part of the study, and together they're like a big supercomputer. They run them over and over again. Okay, I want to go back to lingo again, so that a contingency outage that you didn't plan, outage not planned, okay, is called a forced outage. Forced outage. That's the terminology that all power system people, at least in the United States, use. They call that a forced outage. And there's some rules, and this was in the lecture notes, but I'm going to go talk about just real quick. It's called the N-1 rule. It just simply says N-1 rule. And that is that one component out will not result in an overload or a voltage violation. Okay, and similarly for a generator. So we have to we monitor the system so that we can build a model of it. Then we do our contingency analysis as fast as possible. Okay, then later on the question comes up, well, what if an outage will cause a problem? Now, it hasn't happened yet, but our model says if it does, we got a big problem. Well, now that we come into what's called corrective action, and that's a topic for later on in the course. In the lecture, we showed some really stupid, simple. Again, I like to have real easy examples that are kind of dumb, frankly. But I had this example: 1,200 megawatts, and I had a 500 megawatt generator here and a 700 megawatt generator here, and I had two transmission lines that could carry that 500. So this is max. Now, what determines the maximum power carry capability of a transmission line? It is probably the transformers at either end, unless there are no transformers, in which case it's just the wire. And it may be on a hot day, how hot is that wire going to become? Well, let's say we lose the top wire, the top one, and the circuit breaker is open, and now 500. This is the we're assuming that these can just carry this. So now 500 all comes down here, and you got 500 coming in through here and 250 capacity. And I can tell you what would happen there immediately. You'd get this. Everything opens up. This thing goes offline. And now I have a 700 megawatt generator trying to supply 1,200. And if you don't do anything, this guy will go offline, or you better shed 500. You better shed 500 to reduce this to 700. So you've really got yourself in, So if you have an outage here that results in 500 flowing on this, so this line is carrying twice what it should. Here's the generator and the 1,200. So that 500 going through the 250, you're dead, and this one's going to open. And when it opens, this generator will go offline right away because its frequency will start to go up. And this generator was going to start to go down the frequency, and you better be able to shed load fast, or else the whole thing goes down. That's a blackout. Well, that's a dumb example. It might occur to you to say, who would build a power system with just enough capacity to carry the generator, and if you lost one, you'd have an immediate overload? And I agree. That would not be a good design. That would not be a good design. So you'd want it so that if it lost, that you'd have enough capacity so the generation could still be pushed through the system. And that means it's got to have enough redundancy. And one way of doing that would be this. 3 lines. There you go. 1200, and these can take 250, 250, 250, and this has got a 500. I could lose any one of those lines, and I'm still okay. Transmission lines are expensive, believe me. They're very expensive. You don't want to have to build a transmission line unless you have to, but you want the system to be secure, to be reliable. The rule in the United States was, and I'm sorry folks, I meant to do this ahead of time. And if I don't do it, you can see what happens. I just start lecturing down the page and forget that I'm on the bottom, and I don't, the TV is, the video camera is not seeing it. Okay, so, there we go. If we now, well, let's worry about generator outages later on. I want to talk very quickly about reactive power. Remember that we said that a transmission line has an inductor and a resistor in series, and it also has capacitors to ground. These represent just simply the capacitance between the line and the ground itself. You can put this down here and draw the ground like this. There's no physical capacitance, it's just the line, the wire, and the ground itself. There's a capacitance. And so there's a reactive loss on the line. The loss that goes out here is called I squared X. There's a current coming in here through I. But we also gain capacity, reactive power. And the gain is V squared times the susceptance of the capacitor. And that's at let's say this is I and J. So this is at I plus V squared J, B cap. So the total loss is equal to the sum of the I squared X on the system minus the sum of the V squared B I plus the sum, let me put a minus sign there, V squared J with a B. Now, the problem with this is that when I lose a transmission line, okay, and here we go, back to our simple example again. We've lost a transmission line. So let's say so this is with this line out. And initially I had I flowing here and I had I flowing here. And now I lose this, and so this I goes to 0 and this one becomes 2I. Well then I squared X becomes 2I squared X, which is equal to 4I squared X. So the amount of reactive power that this second line is drawing is 4 times what it was when both lines were in, assuming that they had equal current. It goes up by 4 times. What's worse is that the voltage, and by V I mean the magnitude of the voltage, begins to go down. Let's say at this end it stays the same. So the loss is I squared X. That goes up times by 4 to 4I squared X, and the voltage at the J end here Vj is lower, so the V squared J be, and it's not going to go up down by half or anything like that. And so this is now smaller. Remember, this is a negative term, this is a positive term. So the amount that's been subtracting off because you got some reactive coming through the capacitor is not as great. And the result is a large demand for reactive power. And that comes from generators, from Q, from generators. Let's say we have a generator here too, Q. So you have an outage and you have a large amount of reactive power, and that reactive power just kills you because the generator can't supply it. The generator has lost its ability to supply reactive power to the power system. Okay, so now for the remainder of the course, the problem session, I'm going to show you an example system. This is a purely made up academic exercise system that I made up many years ago. Here it is. I got the diagram. You can see this. It's printed in your book, and this is the reference bus here. We'll just write ref. So I have 3 generators and 3 loads, and a bunch of transmission lines. Let's see, 2, 4, 6, 7, 8, 9, 10. So there are 6 buses. It's actually 11 lines. So this is a very dense system as far as the number of lines. And you're going to have to learn how to use the MATLAB programs, because they use a spreadsheet. There's a user manual, very thorough user's manual in the CUSP. They're called labs. And the homework will use the software that's in there. And there's a contingency analysis program. Here is what I did. I took the base case loads, and I just call that the base case, and each load equals 100 megawatts. So the total on 3 of them is 300 megawatts. And then I came back and I said, well, I'm gonna multiply load by 1.5. So I'm going to have a 50% increase in load, so that the total becomes 450 megawatts. There's 150 on each bus. And it turns out I programmed it so there's a simple variable called case multiply. Case mult, that's the name of the variable. And you look in there, there's a place to set that variable. And what you do is you open the network data file, and you set case mult. Oh, you open this data file in Excel. It's an Excel spreadsheet. And you set this to equal 1.5, and then you save it. Save it back to the hard drive, back to your computer hard drive. so that you've changed this value. Now the reason you have to save it back is so that now when you run the program, it asks you what file you're going to use. So you tell it, in this case I told it the 6-bus case. So okay, so I ran it for the base case, where case mult equals 1.0. I ran it for the next level, where case mult equals 1.5, and then I just took the power system and I said, we're going to see what happens to this poor little power system, and I'm going to have an extreme peak load. Case mult equals 2.0. So in this case, we go to 600 megawatts on that system. And then it's going to start running outages. It just takes them one at a time. One transmission line, takes it out, puts it back, takes the next one, and takes it out, does the study, puts it back, and so forth. Two things that I want to indicate to you is that we developed and I can't claim complete, this is not all my idea, but we developed something called a performance index. What I'd like to know is, when I have an outage, is the power system in trouble? And here's what we did. We said, okay, all lines, now that means all lines that are operating, we're going to take the flow on the line L, so all lines L equal 1 to whatever the number of lines, okay? The flow L divided by flow L max. Okay, and we're going to take this number. A lot of initial work, we raised this, but I'm going to say to the 2n power. Now, if you make n a number like 3, 2 or 3 or 4, you are raising that to a huge exponent. So here's what happens. Here's the line flow here. And here is flow L over flow L max. So here's the max right here. If the flow is here, so it's 1/2 of this. So this is 1/2 of the max, then this is 1/2. All right, if you raise, let's say you use n equals 3. So then I'm raising this to the 6th power. Well, 1/2 to the 6th power is a very small number, right? It's what, 1 over 32. So it gets to be a very small number. So this term here to the 2n is a very small number, and it doesn't move much until you get close to the max. And when it gets to the max value, here's 1.0. Otherwise, it's very, very low. It's the further down you get. If it's 0.1, well, then it's 0.1 to the 6th power, which is some, 0.0000, etc. 1. It's just very small. I didn't draw it very, but it gets to be, and then it goes like this, boom, up to the sky. So if it's 1.1 to the 6th power, 1.1. So it's just 10% overloaded. I can take my calculator here and I can say, okay, 1.1 times 1.1 times 1.1. That's 3 times 1.1. That's 4 times 1.1 equals the sixth power. It's 1.7. And if it gets up to 1.2, if it's 20%, this term just goes real high. So this is the theory of it. Now, there's lots of problems with this, but let me just say, I'll put it this way. In theory, if PI is low, system okay. If PI is high, system is bad. I'll just say that. System's got lots of overloads, the transmission lines. So all I need is a couple of lines overloaded, and if I sum over the whole system. And so we're going to show some results here for that 6-bus system when we're doing line outages. And I did it for 3 of them, and I don't have to I don't have to show you all 3. But let's just start. So I put the diagram over here. There it is. So my first outage was 1 to 2. So here's 1 to 2. So the first outage was here, 1 to 2. This is the 1 to 2. The next outage was 1 to 4, and that's just because of the way they're ordered. There's 1 to 4, and then 1 to 5, which is this one here. 1 to 5. So I did this outage, then I put it back, then I did this outage, put it back, then I did this outage. Well, let's see the kind of things that happen. In the base case, and that's where C case mult equals 1. So I'll put the load up here, 300 megawatts. Okay, and we'll build a little table. Then we had case mult 1.5, which gives me a total load of 450. And then we'll do another one, which is case mult equals 2, or 600 megawatts over here. Now I'm gonna show you the case for line 1-2 out. Okay, base case. This is base case load. Okay, line 1 to 2 out, and I'm gonna show you the PI for the flows. You look back in the book. There's also a PI, a performance index for voltage. It's a little more complex, but it simply involves subtracting the voltage from either its upper or lower case or lower value and raising it to a large power. So there's PI flows, there's PI voltage, there's the worst overload, there's the worst voltage violation. Now, if a voltage doesn't go outside its limit, then I don't consider that to be a violation, if it just moves between limits. And I'm going to show you the lowest voltage. Okay, so at 300 megawatts with line 1 to 2 out, the PI flow is 11.8. The PI for the voltages is 7.0. Now, what you're going to see is that the PI for voltages, because voltages don't move much. They move in small percentages, and we worry about a 5% change. Whereas flows could double. So you're going to see that this is very volatile here. This changes, but not by much. The worst flow overload is 20, and that's in megawatts. There's no voltages that go over. And the worst voltage, now we're talking about per unit, so I'll just put 0.99. Now per unit, think of it as a percentage. It says that if the nominal voltage is 1.0, then this is 0.99 per unit. You need to study power flows. You know, we do everything in per unit. But think of this, it says, all right, the worst thing that happened is that a voltage went from a value of 1.0, its nominal value, it went to 0.99, which is a 1% drop. Okay? Now look at the same outage at 450 megawatts. Now the PI here gets to be 1,003. This thing goes to 704. It doesn't move much, but the worst overload is 90. This is in megawatts, and again, we don't have enough. We don't have any voltage violations. The worst voltage drop is 0.98. So it seems to hold up, although we've got some severe, we've got some overloading that's not very good. Now we go to 600 megawatts. And when I did that, this thing goes to 34,183. This thing goes to 7.5. Now you're starting to get some movement in the PI for the voltages. The worst overload, 175 megawatts. Well, that's you're going to melt the line. And the worst voltage shift, I'm not sure. I got to 1.89. I think that's. I'm going to put a question mark. I'm not. I got to look at this and maybe explain it or get the program going a little bit. But the lowest voltage is 0.93. So this is down 7%. And if we're worrying about 5%, a 7% voltage drop, the system is in trouble. It is in real trouble. I was giving a lecture one day to one of our Center for Electric Energy companies, and there was a fellow in there from the operations group, kept getting up and walking out in the hall, and then he kept coming back in. I said, is something wrong? I thought, maybe his wife's going to have a baby. I don't know. I didn't ask him that, but I said, what's wrong? Well, he says, we've got this, he said, this is a very hot day, and it was the middle of the afternoon, and he says, we're watching the contingency voltage at a certain point, which happens to be not too far out of the Minneapolis area. And he says, it's just the contingency voltage is dropping, and maybe it was like 5 or 6%. It was just on the edge of disaster. And what they would have had to do is that they would have to go into the market and say, okay, don't transfer so much power from one area to the other. And that meant that they would have to pay more for power. But he was worried about that contingency voltage, because he said, if we don't pay attention to it and we get a contingency and the voltage drops to that, the system might collapse. So, and I've noticed that before. Power system operators, the power system is like, it's like their baby, and the baby is on life support, and they don't want the thing to go. Now let's see, 1, 2, 3, 4, 5. 3, 4, 5. I can. So now I'm going to do another outage, just to show you what happened. Now I'm going to take line 1 to 4 out, okay? And I'm going to have you run this same program to go over the results. But now the PI flow gets to be 146. The PI voltage gets to be 704. That's not that bad. The worst overload is 55 megawatts. The worst voltage deviation is 0, and the lowest voltage is 228. I don't know. It's like 0.99. It doesn't really matter. That's for 300. And now for the 450, this thing shoots all the way up to 11,415 just for the 450. This goes to 7.43. That's a very severe outage. This is 139 overload. This gets to be 0.93. There's your 7% again. What about at 600? Well, this becomes a ridiculous 36 times 10 to the 6th. I told you it would explode. It means I've got lots and lots and lots of overloads here. This thing becomes 116. It's no longer near 7. The worst overload is 431. So I mean that shows you how much that could be. And let's just say that the lowest voltage is 0.68. 0.7 would be 30%. So that's down 32%. People, if you have a voltage that goes down by 10%, your system is probably going to collapse. Okay, maybe not, but 10% voltage drop on a bus someplace, your system is in real trouble. Believe me, a 32%. So what this says is that at 600 megawatts, this system is going to die if I lose line 1 to 4. Now, if it's possible to hit 600 megawatts while you're operating the system, you're in trouble. You haven't built the system right. So you'd like to know that way ahead of time. Now, generally, if you're looking at 300 megawatts, the online load is not going to shift by a factor of 2. It's going to shift by small percentages up and down. And it might be higher than it was last summer. And so they try to estimate the peak, and they do risk assessment where they say, well, okay, here's the load. Now, we forecast the load to go up by 10% next summer. But it might go up to 12% with a small probability, and it might go up by 15% with a much, much smaller probability. And we try to do some risk assessment around the load so that we can look at the probability. And you better have contingency abilities in there, or you're going to have a great deal of difficulty. I'm going to give you this. This was my original data. I don't have time to go through the rest of it here, but I'm going to give you the printouts, results. They'll be tacked on to the notes for this session, so you'll be able to see it. And the name of the program, we'll put it in here. Under the security analysis, it's called run_AC power flow _contingency_ANAL for run AC power flow contingency analysis. These are underscore characters because you can't put a space in the middle of a MATLAB variable name. But if you want the variable name or the program name to look like it has multiple words, then put underscores. So these are underscore. That's the program. And for your homework, I will explain a little more about how to use that program. But that was a demonstration of what happens when you overstress the system. The lesson to be taken from this is that higher loads could be the death of your power system and a blackout. And if you're the chief engineer and you suffer a blackout, you're in trouble. I know that there was a blackout. I believe it was the late 1990s in Malaysia. That's the country that's just above Singapore, below Vietnam. It's a very advanced country. The capital city is Kuala Lumpur. I have been there. Beautiful city, absolutely beautiful city. They have what they call the Petronas Towers, which is they were at the time being built, the tallest buildings in the world. Very modern. They had a blackout. Later on, they figured out what the cause was. And I read some papers about it, and I actually talked to some of the people when I was in Kuala Lumpur giving a course. At the time, and the reason I'm chuckling here, it's really not funny for the person concerned. It was a government utility, and when they had the blackout, the person who was in charge was fired. That was it. Who's in charge here? Well, I am. You're fired, okay? And that person lost their job. To my knowledge, they weren't sent to jail or anything, but that's the danger that you could get into. So you will see. I will give you all these results, and you can go through them. I'm going to check the programs tomorrow, but we're going to have you do some of this for the homework. The next homework 06, which will come to you after the midterm exam. Okay. So we will start our shutdown here, and I will say good night.